Okay, great. Let's get started. So, welcome everyone. My name is Heikki Verta. I work for Supercell. I lead the services team there. And I'm going to talk to you about scaling our mobile games and our analytics. But before we start, could you raise your hand if you work in the gaming industry? Okay, cool. That's more than half. I gave this similar talk like a week ago and asked the same question, and out of 100 people, there was like 8 from the gaming industry. But don't worry, even if you are not from the gaming industry, this is a general presentation which is applicable to your domain as well, I hope. Yeah, my background is in server development. I used to work for Unity before joining Supercell and FutureMark. It's a sort of niche benchmarking company before that, and then of course Nokia. Been at the industry for something like 15, 20 years. But let's get going. I roughly have 3 topics that I want to cover today, and I'll start with the Supercell sort of team structure and culture part, and that's because it sort of has implications on how we do things. So I want to cover that first. Then I'll talk about scaling our games, and then on the second half about analytics. But let's start first with a quick intro about the company. So we're a mobile games company founded in 2010 in Helsinki. We have offices in Helsinki, Shanghai, San Francisco, Tokyo, and Seoul. Game development happens in Helsinki, but also in Helsinki, and there's a small team in Shanghai as well. Right now we have 4 games live. You can see some of the characters there. There's Clash of Clans, Clash Royale, Heyday, and Boom Beach. And actually, pretty soon, there's a 5th game coming up called Brawl Stars. It's in soft launch now, but we're gonna launch it globally soon. It's a new kind of game for us. It's a 3v3 MOBA sort of real-time battle game, which has some interesting implications on the server side as well. On sort of to give you the background, so on a super high level, this is sort of the challenge we're facing. We're going to have 5 games with hundreds of millions of active users. At peak times, we see some 4 million concurrent users. We run approximately 6,000 EC2 instances on AWS, and scaled to, those are all kinds of different instance types. So scaled to the X large capacity, it's something around 20,000 instances. We also run lots of databases, so I'll talk about that. Our games are run on MySQL and on EC2. We run something like 300 databases with a master and 2 slaves, so that's a lot of machines as well. But the company actually is pretty small. We are a 250 people company. Our teams are also pretty small. So in a live game team, there's approximately 20 people. And out of those 20 people, 3 are server developers. So that our challenge obviously is how do we operate and develop our games at this scale with so few engineering efforts, resources. And that's where we come to the culture part. So basically, we believe that this is a super condensed version. So we believe that the best teams make the best games. So our teams are cross-functional and vertically aligned. So that means there's a server developer, client developer, QA person, game designer, artist, data scientist, everybody at the same team. So we're not spread out sort of horizontally by function, but by product. these teams are actually also super small. As I mentioned, something like 20 people. We also work sort of bottom up, not top down. So there's very little top-down management. The teams are the top-level entity, not senior management. The teams, they are fully trusted to own and execute their own vision. So they have a high degree of independence, but of course, responsibility as well. So they're responsible for making the best decisions for Supercell, and especially the hardest ones. In a nutshell, we sort of optimize for passion and speed, not control. And if I had to put this in sort of one word, I think it would be agile. So, and agile in the software development sense, but applied to the whole company. The implications of this, of course, on the AWS side is that since the teams are super independent, they also own their own AWS accounts. The top-level structure there as well is by product, not by service. The environments are mostly split into separate accounts, but of course there's billing, support, and all of that that's consolidated. There is no separate operations team. So the teams practice DevOps. They set up, maintain, and operate their own cloud resources, and all server developers participate in the on-call rotation. The teams are free to choose their own tech stack, so we don't have a quote-unquote Supercell platform that the teams have to use. In practice, though, as we have sort of a battle-tested environment, it's sort of, the game environments are pretty similar. There's differences here and there, but overall, they're pretty similar, and what that looks like, you'll see soon. The variation is greater than in the other functions like analytics, machine learning, support, anti-fraud, live ops, and stuff like that. An important part is also that we use AWS managed services to reduce our ops burden. So we are not cloud agnostic in that sense. We believe that's something. If we come to that bridge that we want to switch providers, we'll cross it when we get there. So we try to minimize our own ops burden now by leveraging the managed services that AWS provides. But that's sort of the super high level background. Let's dig into the games. And just to kick things off, this is the super high level game stack. Very similar, very traditional client server. So there's a OpenGL C++ client that runs our own engine. It communicates with the server using a custom binary protocol over TCP and UDP. The server is implemented in Java, and we also use Zookeeper to manage the cluster. The databases are running MySQL on EC2, so we started before RDS and all of that. So our deployment is actually still on EC2 instances with the Percona flavor of MySQL installed there by ourselves. We also use, in the newer game, Brawl Stars, we are using RDS Aurora, and I'll talk a little bit about that. And then we also use DynamoDB for some data sets like the replays and stuff like this. So let's talk about how do we scale that stack. And I think it sort of comes down to this. So scaling in the cloud is about scaling out, not up. So not a bigger machine, a bigger machine, and a bigger machine, but more machines. And I actually believe that the sort of technology and the algorithms you use matter much less than the overall architecture of your system. But okay, fine. So how do we enable this? For us, it comes down to two things. First of all, a microservice architecture. That's for the business logic of the game cluster, and then the sharding of the database layer. That's for the persistence layer. And if we take a look at the microservice part first, or the game cluster deployment first, so the games are split into services. So instead of a single monolithic application, the game cluster is split into independent services like proxies, home containers, battle containers, account directories. There's something like, I know the guys know the exact number, but there's something like 15 different kind of services. These run on different instances, of course, and communicate over the network. But it's not like a true microservice architecture in that sense, so I'd actually call it a microservices light architecture, because the game is developed as a single artifact. It has one repository, one programming language, that's Java, and one team. So in that sense, it's not a traditional microservice architecture, maybe more like a distributed architecture. And the way we scale out that architecture splits into two dimensions. So the first is Amazon EC2 autoscaling that handles the scaling of the actual EC2 instances. Then the other direction is Zookeeper, which is an open source server for coordinating distributed applications that handles the different roles that the servers then take in the game cluster. And we need to do this. So in a traditional web application, you normally don't have these two dimensions. You can get pretty far with autoscaling as well by pushing all your state away from your servers. But actually, in gaming, it's all about state. So when you're interacting with the game, you're constantly making changes. So there's a lot of writes. So most of our server load is actually writes. So there's a lot of caching, and that means there's state everywhere. So the state lives all around the cluster. And for that, we need coordination. And that means Zookeeper. So on one side, the autoscaling groups the instances by instance type and security group, and then on the other, Zookeeper assigns them roles. And so what happens when the load increases? The autoscale, there's a bunch of coordinating software in the cluster that scales instructs the autoscaling groups to increase the number of EC2 instances. When those instances come online, they boot into a sort of hot spare state and compete for a role from Zookeeper. And then Zookeeper increases the number of roles. For example, let's say battle containers. So instead of 50, now we need 55. And then those new EC2 instances compete for those roles and boot into that state. This on your right, the image illustrates that it's from a development environment, or a load testing environment. But the green line indicates the sort of load factor that we calculate, and the yellow is the number of instances and how they go up and down. On the database side, as I mentioned, the scaling comes down to sharding, and by sharding here, I mean sharding in a technical sense. A shard for us is a database instance, master and two slaves. It's not some gaming companies when they talk about sharding, they mean that there's a shard of the game for the US market, or there's a shard of the game for the Chinese market. So I'm not talking about that. This is a sort of a strictly technical term that, or in a technical sense that when we talk about sharding, and so each of those shards is an instance of a MySQL database. The schema on all of them is the same, but the data is different. So as new accounts are being created into the cluster, we add new shards, and the new accounts are created there. The balancing of load happens by controlling where new accounts are created. So as new shards come online, we sort of skew the weights of the new account creation towards those shards. So more accounts are created there and less on the older ones. And the existing accounts, they stay where they are. So they are not moved between the shards. And this happens, so this is not automated. It's something that we monitor, and if we need to do, we do manually. And as I mentioned, the shards don't affect the gameplay. So everybody can play with anybody. The games are global in that sense. The one part of sort of failure recovery that we haven't sort of tackled yet is the MySQL master node failure, which still breaks the game for people on that shard. So the accounts, the alliances, the wars that are stored on that accounts. And these are failures that we still have to handle manually. But as I mentioned, for Brawl Stars, we are using Amazon Aurora, and we've actually seen some pretty good results with the auto recovery of Aurora there, and we are looking at migrating some of the current games to Aurora as well in the future. So that's about the gaming part. Then let's take a look at analytics. So again, a quick sort of overview on how we think about analytics at Supercell or data, and it sort of comes down to these points. And I don't believe that, or we don't believe that analytics by themselves can make a hit game, but they can improve it. So in that sense, we're not a data driven culture, but I'd prefer the term data informed. We also have full transparency with regards to data inside the companies, and the data scientists, as I mentioned, are embedded with the teams. So there's no separate data science function as such, but the data scientist for Clash Royale sits with the Clash Royale team. The data scientist for Clash of Clans sits with the Clash of Clans team. In general, so with regards to scale, we receive something like 5 terabytes of data per day, and that 5 terabytes of data contains something like 15 billion atomic rows or events. The total size of our data warehouse is somewhere around 4 or 5 petabytes. And those events, they're just very simple blobs of data, which actually don't contain that much context, so they require further processing. The data volumes actually used to be something like double, but we've pruned the relevant data and used some sampling there. But so actually, when it comes to I think the same goes for gaming, but also for analytics. So I don't actually believe that there's one right answer so that, oh yeah, this is how you should do an analytics pipeline or data warehouse on AWS. So it all depends on your scale and your needs, and so that's why actually I sort of wanted to tell you our analytics story, and hopefully that'll sort of inform you as you make your choices. So this is the rough timeline, but and we'll start first on the top part with which is the data pipeline side. But before we go there, this is actually where we started. Originally, we didn't have a data, quote-unquote, data warehouse at all. We just queried the game databases, and that's it. But as the games evolved, and they of course, the game databases are a little different, the schemas are a little different, so we thought, like, okay, hey, we need to pull this thing together. And the first thing we did was like, okay, yeah, let's install ClickView, load the data in there, and do some processing, and that's it. And yeah, that works. It's super simple, but it suffers from a couple of drawbacks. And first of all, ClickView is a Windows software, so it's a little not as nice to host. It also has its own sort of funky syntax that you have to use, so it's sort of not your ANSI SQL that you use there. It's somewhat slow. The process is, of course, also pretty slow because only and you see only the database state. So whatever is in the database at the time that you loaded it in, that's what you see. And the data is locked inside ClickView. So it's not the ideal solution, and the games were growing, so we needed a better pipeline and a data warehouse. And I'll talk about the pipeline part first. And the first thing we did was like, okay, so we only see the game database state, so let's add events. Whenever something interesting happens in the game, let's send an event and collect that. And we started from the client side. So the events are sent via HTTP to a collector cluster, simplified here, of course, also. There's a sort of a collector process that receives the data, stores it locally, then batches it up and writes to S3. And it took a little engineering effort to get all this receiving and processing done, because the scale at the time when we only had these client-side events was pretty large, something like 10 terabytes a day and 60 billion events. But the main problem actually with this approach was that it suffered from poor quality. So we wanted to get rid of the integrations with the game databases. We wanted to calculate all our KPIs from the event data, but the quality really wasn't there. So there was duplication, we were losing data. And we wanted to achieve sort of the 1 promille accuracy, which we weren't able to hit with this solution. So then we decided that, okay, we can't trust the clients, so let's send the events from the server. And we added a server event layer. And here actually we also changed the protocol, so we started using UDP, which we did because we were a little bit afraid of the impact that this would have on our game servers, and we wanted to minimize that, so we went with UDP. I think now it could be TCP or something, a stateful protocol as well. But this was the solution at the time, and it's actually stick around. So this is something that has stuck around. Still the sending goes through UDP. And with this approach, we got the sort of accuracy that we wanted, as long as the sending and the receiving happens in the same region. So we were happy with that. And so there's this sort of event pipeline, as we call it at the time. It's again super simple. We gather much more details about not just about the accounts, not just the database changes, but there's still something missing. So we don't have real-time access to the data. The data is in the pipeline until it magically appears in S3. Also, if there's a failure, the data lives in local disk for a while, so there's a risk of losing the data. And the only way to consume that data is by reading S3. So Amazon at the time, like late 2013, started testing Kinesis in beta, and we took that into use pretty early and added that as sort of a buffer layer between the receiving and then the storing. And we kept sort of the store and forward layer of the collectors for control and extra redundancy and a little bit of enrichment and validation that happens there. And the reason why we chose Kinesis instead of Kafka, for example, which is another very popular streaming data solution, is that it minimizes the operations and maintenance that we have to do. It's basically you go to the AWS console and click, you get a stream, and you don't have to do anything. It's super nice, and it gives us sort of 80% of what we need with no ops. And I'll come to what the missing 20% is a bit later. But anyway, so the data goes in between goes to Kinesis, and from Kinesis it's read out and written this time in LZO into Amazon S3. Very similar to before, but the key thing that Kinesis adds here is real-time access, streaming access to the data, and this actually unlocked a lot of new use cases. So we use this real-time access to the data to update search indexes, do real-time analytics, integrate real-time with ad vendors, for example, and do a bunch of support use cases. And all of this we sort of call roughly speaking, the streaming pipeline. And the benefits are pretty nice. So the data is safe from local failures. There's a lot of redundancy in Kinesis, and AWS takes care of that for us. We also get real-time access to the data and multiple ways of consuming data. So not just reading big files from S3, but also the streaming aspect. Our Kinesis setup is roughly this. There's two main streams. There's a stream for client events and a stream for server events. And these streams contain all kinds of data, so all types of events. So logins, transactions, battles, all kinds. The data, so Kinesis gives you sort of couple of guarantees, like at least one semantics for your events and ordering, as long as you use the same partition key. But actually, we don't do that. So we use a random partition key when we write the data into Kinesis, and we, of course, lose the ordering. But what we gain is the uniform load between the Kinesis shards. So again, the term shard here, this time, it means a Kinesis shard. So that's a unit of scaling that Kinesis uses. And the ordering is actually not a sort of losing the ordering, so that the events can come in a little bit in different order is not that bad for data warehousing and analytics when you do sort of batch processing. But it does complicate a little bit the situation in the real-time world, in the real-time applications. But we've still taken this sort of a trade-off here. And we use the KCL, the Kinesis client library, of course, to consume the streams. It's actually non-trivial to consume a Kinesis stream, but the KCL makes it a lot easier. And this is the 20% that we still feel that is missing from Kinesis. And our challenge here is that the main streams are quite large. They're not huge, but they're relatively large. So some hundreds of shards, quite a lot of data going through, and they contain multiple types of events. But not all clients are interested in all of those events. This application only wants the transactions. This application is only interested in player name changes or something like that. And they have to now from the vanilla Kinesis, they have to read everything in. So what we've done in between is sort of a Kinesis application that dispatches, splits this mainstream into application-specific streams, which we have, I think, in total something like 50 different streams. And these streams contain only a subset of the events, so only the events that application is interested in. And that sort of completes the picture. That's basically where we are with regards to the data pipeline at the moment. And so let's take a look at the data warehousing side. And as I mentioned, we started with ClickView. Had a little bit of trouble there, and our first iteration was to just let's get rid of that and let's use a distributed or a clustered columnar database. Just put everything there, do the ETL there, and that's it. So we chose Vertica, and added Azkaban. So Azkaban is one of those workflow managers. It's created by LinkedIn, but similar to Airflow. It orchestrates the ETL process, or the process. It loads data from S3 into Vertica, and then the ETL happens inside Vertica using SQL. And everybody just queries the dashboards, the data scientists query database, query Vertica with SQL. And this is a pretty nice setup because you get a single source of truth. All the data lives in Vertica. It's easy to query with SQL. And this worked well for us for roughly the sort of terabyte to tens of billions of rows of data. But there are a couple of challenges with this approach, and I think the first one is, of course, that you get a spiky load on your cluster. When your cluster is doing the ETL, it's running super red hot. When it's not, it's idling. And when it's running the ETL, the querying is really slow. So it's not really optimal usage for the database. Also, Vertica is not, as they say, sort of cloud native. So we do run it on AWS, but it takes a little bit of effort to scale up and down. And we've done it a couple of times, but sort of have refrained from doing it nowadays because, again, the teams are so small that we don't really have the resources to dedicate people in maintaining or scaling the Vertica. And also storage and compute are tied together. So if you need more storage, you're gonna increase your compute power, and if you need more compute power, you're gonna increase your storage as well. And as the incoming data was growing, even a columnar database cluster like Vertica does have its limits. So we started thinking like, okay, so how could we sort of fix these issues? And our goal was to sort of limit the amount of data in Vertica. We had scaled it, I think, 2 times already. We didn't want to do the third one, again doubling the size of the cluster. We also wanted to separate compute from storage. So if we needed more compute power, that's fine. And if we need more storage, that could be a separate issue. And we wanted to separate the ETL processing from the querying processing, but maintain the single source of truth and utilize the flexibility of the cloud to get rid of that spiky load problem. And sort of this is the plan that we came up with. So instead of Vertica, use Amazon S3 as the single source of truth, write the data and store it there as Parquet, and use Amazon EMR for ETL, not Vertica, and only store the results in Vertica, so the accounts, the aggregates, and the KPIs, not the raw data. And this is roughly how it looks like. So again, Azkaban controls the ETL process, but this time the heavy lifting is done in Amazon EMR by Spark and Spark SQL. The data is read and written back to S3 in Parquet, so that the final format is in Parquet, and S3 is the single source of truth. It contains all the data, the raw, the atomic, the aggregate, and the KPI level of data. Then only the aggregates and KPIs are copied to Vertica for easier access, and the atomic data only lives in S3. Then during the ETL process, we also populate the Glue data catalog with the new partitions as they come in, and that allows us to use Athena to query the data, and also Amazon EMR. And then the querying happens through all of these 3 options. So data scientists may be using EMR, then dashboards, BI tools connecting to Vertica, ad hoc queries running in Athena. And this gives us easy SQL-like visibility to all the data, both for data scientists and regular users. And Athena is there in the middle, and it's actually it's a really nice service for your ad hoc queries. But it actually is not. I wouldn't use that for your sort of day-to-day BI dashboarding needs. It still is limited. It has some concurrency issues, and also it struggles. It's based on Presto, and that struggles with the schema evolution of complex data types. So it's a little bit limited. So that's why we've kept Vertica there as the main sort of querying database. But Athena is super nice for your sort of ad hoc queries that you need to do. And this approach gave us some nice benefits. So again, now we've separated out compute and storage. So storage is in S3, compute on EMR. So we don't use HDFS there. If the data grows, if the workloads become more complex, we can scale the EMR clusters. Also, Amazon EMR scales out to super large data sets, so we haven't had a problem with that. And we can use dedicated and transient clusters for the ETL workloads. So when the ETL process is running, we spawn a cluster, and when the ETL job is done, we tear it down. So no need to run idle clusters anymore. And as an extra benefit, EMR is a familiar environment for our data scientists. There's sort of a couple of tips that also with regards to EMR that if you're not using HDFS but you're using S3, you might sort of run into this sort of eventual consistency problem with S3. So if you have one job that writes data to S3 and then the next one wants to read that, it might not see it, even though the data is there, but it might not see it. So there's sort of a workaround. I almost said hack, but a workaround that AWS has done with this sort of consistent view feature that uses DynamoDB to keep track of what files are where, which sort of helps you work around this. But it's not the ideal solution, but does help you with that. We've also done a little bit of customization on the AMI that we use to get faster startups for the clusters and all of that. So that sort of completes the picture also from the data warehouse side. So we've gone from game databases to ClickView to Vertica to S3, and okay, so what have we learned? I think for scaling and failure recovery, as I mentioned, I do think that scaling is determined mostly by your architecture. The technology, the architecture, the algorithms that you use, they are important, but it's mostly about your architecture. And also, you don't need super fancy tech to scale. You can just, by focusing on the fundamentals, you can get far. So our stack is actually super simple. It's MySQL plus Java plus Zookeeper on EC2. And we run a game cluster of thousands of machines with that. Microservices and DB sharding, database sharding, also gets you far with regards to scaling, but of course it's not free. Microservices bring with them their own benefits, but also their costs. So you need to think about retrying your requests, logging, debugging, all of that becomes more difficult. But it does break the application into sort of more scalable units for sure. And a third thing is of course that it's the cloud, so assume that things fail and take that into account. It's sort of a basic thing you can do, and it gives you a lot of benefit for as you go forward. And it also makes your infrastructure a lot easier to update. For analytics, I think separating your compute and storage is key. So it makes scaling a lot easier. It unlocks a lot of new use cases, especially with regards to real-time access to the data. And also, everything starts with I believe, with the fundamentals. So reliable and scalable data is what you should do first. Then think about the higher level use cases, so machine learning, BI tools, dashboards, and all of that. Those are important, but all of those rely on good data, so start with that. And schema. So we actually, as you noticed, there wasn't a lot of mention about schema in those slides, and we actually don't have a really good solution for that, so how to define your schema. So we've shied away from automatic schema discovery because of the complications involved there, but you still need the schema in a lot of places. So take that into account. And also, finally, don't have a data police. So, and what I mean by that is a single place that needs to sort of approve, through which your data requests need to go through. So we actually started with that, so we had a definition of what the events are, and there was a single library that contained all of that, but that quickly became the bottleneck. So the way you get the most benefit out of your data is to make it super easy to produce and consume it. So just make it simple for people to access and create data. And then for the culture part, I actually do believe that the best thing about Supercell are the independent teams. So you can get a lot done with small and independent teams. There's much less need for processes and bureaucracy and politics and all of that when the teams are small. And also, I think the proof is in the pudding that you don't need a large centralized engineering team to run global games. But at the same time, I actually also believe that the most challenging part about Supercell are the independent teams. So there's a lot of benefit, but there's also, with that sort of degree of agility, there's a bunch of chaos that's created when there's less centralized control. And a particular challenge here are things that fall sort of in between the teams. So GDPR, for example. So that is a sort of thing that concerns everybody, but it's not really any game teams or another team's sort of responsibility. So how do you handle that in a setup like this? So there are some challenges as well. But I do believe that the benefits far, far outweigh the costs. So the speed, the impact, the sort of empowerment the developers feel is much greater than the costs. And that's it. Thank you. So my name was and is Heikki Verta. You can find me here for questions and answers, and the slides and the video will be available at SlideShare and YouTube. And please do feel free to complete the session survey. Thanks a lot.